Ukraine delivered a vivid demonstration of modern drone warfare this morning over the skies of Belgorod. A first-person view attack drone from the Rarog unit locked onto a Russian Mi-28N Attack Helicopter, closed the distance smoothly, and struck it successfully. The footage reveals a striking scene. The helicopter flies straight and steady, seemingly unaware of the drone approaching from behind or below. The pilot appears completely focused on forward flight, giving no sign of evasive action. This moment captures how difficult detection becomes in the chaos surrounding a helicopter in flight. The main rotor system of the Mi-28N spins at high revolutions, generating powerful downwash and intense acoustic noise. That turbulent air mass and roaring sound create a challenging environment for any small object nearby. The rotor blades slice through the air at tip speeds approaching the speed of sound, producing strong vortices and pressure waves that mask smaller signatures. For the helicopter crew, spotting a tiny drone visually or on sensors becomes extremely difficult amid the vibration, engine noise, and aerodynamic disturbances they create themselves. The pilot likely had no clear indication of the hunt underway until the moment of impact. This brings fascinating aerodynamics into play. As the drone closes in, it enters the helicopter's rotor downwash, a column of accelerated air moving downward at significant velocity. One might expect severe turbulence to throw the drone around wildly, yet skilled Ukrainian pilots and well-tuned flight controllers managed to maintain stability. Modern FPV drones use sophisticated inertial measurement units combining gyroscopes and accelerometers that sample hundreds of times per second. These sensors feed data into flight control algorithms running on fast microcontrollers. The software makes constant micro-adjustments to motor speeds, countering gusts and maintaining the drone's orientation and trajectory. Interestingly, the strong downward airflow from the rotor can actually assist the final approach in some geometries. The downwash creates a region of accelerated air that can help pull the lighter drone toward the helicopter once it enters the flow field, almost like a natural guidance effect. The pilot times the entry carefully, using the drone's own thrust vectoring and agile control surfaces to ride the airflow rather than fight it completely. This demands exceptional skill and deep understanding of both platforms' aerodynamic interactions. The warhead physics adds another layer. The drone carries a shape charge designed to focus explosive energy into a high-velocity jet upon contact. When the drone meets the spinning composite rotor blades, tremendous kinetic energy exchange occurs in an instant. The blades possess enormous momentum, yet the rapid detonation releases chemical energy faster than the mechanical cutting can complete, often fracturing blade structure or disrupting rotor balance before full severance. Material science plays a key role here. Helicopter blades use layered carbon fiber composites with tough leading-edge protection, but they remain vulnerable to precisely timed explosive events at close range. The cost contrast sharpens the strategic picture. A single Mi-28N represents tens of millions of dollars in development, production, and specialized pilot training. Each FPV drone costs only a few $1,000s. This economic reality pressures Russia's military-industrial complex to invest heavily in electronic warfare suites, new sensor packages, and rotor protection concepts, while Ukraine's agile innovation network, driven by volunteers and engineers, iterates designs at remarkable speed. Battlefield implications spread widely. Attack helicopters provide mobile firepower, raw contussants, and close air support that give ground forces a powerful advantage in combined arms maneuvers. When small drones can approach undetected and deliver precise strikes, commanders become more cautious about committing these assets. Helicopters may need to operate at greater altitudes or distances, reducing their responsiveness and overall effectiveness. This shift influences how air and ground forces coordinate in dynamic environments. Geopolitically, the engagement sends a clear signal. Ukraine demonstrates that creative adaptation and rapid technological iteration allow a determined defender to challenge a larger adversary's conventional air assets. Defense establishments worldwide observe closely as this conflict redefines the economics and tactics of aerial warfare. Nations now accelerate drone programs, recognizing the advantages that come from integrating commercial technology and empowering small teams with sophisticated tools. Traditional military-industrial models built around long development cycles and expensive platforms now compete with faster, more flexible approaches. This successful strike over Belgorod adds to a growing pattern of Ukrainian FPV effectiveness against Russian rotary-wing aircraft. The helicopter's crew likely remained unaware until the final moments, highlighting the stealth advantage these small systems possess in the noisy, turbulent environment around large rotorcraft. Ukraine continues pushing the frontier through ingenuity, field experience, and technical refinement. Every engagement like this reshapes how modern conflicts unfold, proving that smart, adaptable unmanned systems can challenge even sophisticated manned platforms in unexpected ways. This is the evolving reality of warfare taking shape in real time.